So we're going to talk about something special in trigonometry called the unit circle. And we're going to talk about defining sine and cosine in terms of the unit circle. So a unit circle is a circle whose radius is 1. And what we want to talk about today is how we draw an angle in a unit circle. So the angles that we say are in standard position are measured from the positive x-axis and turn counterclockwise. Okay, the IB calls it anti-clockwise. So here's my positive x-axis, and I would measure an angle rotating it in an anti-clockwise direction around the x-axis, or from the positive x-axis. So those are how I measure my angles. Now, what we're going to do is we're going to start using cosine and sine in this. So the coordinates of any point on the unit circle can be expressed in terms of its angle measure in standard position. So let's take a look at this diagram here to the right. What I want you to notice is in this green, I will draw a blue triangle because it's blue. In this blue triangle here, notice that we've made a right angle. The angle theta is the angle formed from the positive x-axis in a rotation. And because it's a unit circle, the radius is 1. So then the sine of the angle is the opposite side, which is the y value, over the hypotenuse, 1. So sine of theta is just really the opposite side of the triangle. Similarly, the cosine of the angle is adjacent over hypotenuse. This is my x distance, adjacent over hypotenuse. So this is why we can name a point. Instead of x comma y, we can name it in terms of the cosine and sine of its angle of rotation from standard position. Now, if you go back to geometry, you might remember that the equation of a circle, whose center is at the origin, is x squared plus y squared equals radius squared, or just by the Pythagorean theorem. So really, leads us to this new thing called the Pythagorean identity. An identity is an equation that is always true regardless of the numbers that are substituted into it. And please notice that this equation, sine squared theta plus cos squared theta equals 1, it's really the sine of the angle squared. So the way we write it, though, so that we don't see that we're squaring the angle theta, we put the squared after the sine. So this is the way that it's technically expressed, but we write it with the exponents on sine and cosine. And we say sine squared theta and cosine squared theta. That's kind of the vocabulary behind it. So before we get going figuring out some values, we got to kick back again to these special right triangles. We hit these earlier, and what you might remember from here is that in the triangle on the left, the 45, 45, 90 triangle, that we found that these sides were radical 2 over 2. And in the 30, 60, 90 triangle, remember that angle is going to be 30 up there, that the side opposite the 30 was not 1/3, it was 1/2. And the side opposite the 60 was radical 3 over 2. So we're going to remember some of those values for today to make our lives a little bit easier as well. So why don't we start off with this 30, 60, 90 degree triangle? What we're going to do is we're going to find point A on the circle so that we rotate it 30 degrees from standard position. So perhaps it looks something like this. That might be our 30 degree angle in standard position. So here's my point A. And I'm going to drop point B straight down here. So here's point B. This is vertical, so I have a right triangle here. It's my unit circle, so the hypotenuse is 1. So notice, if I go back to my 30, 60, 90 triangle, what I know is that my shorter leg is 1/2. My longer leg is the square root of 3 over 2. So if we combine a couple things together now, what we know is that segment OB, this side here, is the x-coordinate of point A. So point A has an x value of the cosine of 30. And AB, the vertical side, is the y coordinate. So it could be called cosine 30, sine 30. But what we also know is that the cosine of 30 is the square root of 3 over 2, because that's our distance from O to B. That's the side opposite the 60-degree angle. And the height is 1/2. So what we've just figured out from here is some big things. We figured out that the sine of 30 is 1/2, and the cosine of 30 is radical 3 over 2. That's great stuff. Those are exact values. We don't need a calculator for that, my friends. So here's what we want to do now. Now we want to take that triangle that was at that 30-degree angle. Okay, let me just redraw that one in. It looks something like this, right? There's my 30-degree angle. Here's my triangle. I want to do some reflections and rotations of this triangle. So one thing I'm going to do is I'm going to reflect it over the y-axis. So now it looks something like this. So this angle is still my 30-degree angle. But notice now that the angle of rotation, the angle in standard position, the angle that this green hypotenuse makes with the positive x-axis is now 150 degrees. Because we would go a whole distance of 180, but then we're going to go back 30. So that's where we get 150. Yeah, let me put that 30 back in there. So this point is going to be the cosine of 150, sine 150. And because we know that the cosine of 150, or the x value, is that horizontal distance, in this case, it's negative radical 3 over 2. Remember, when we went in the positive x direction, it was positive radical 3 over 2. Well, now it's negative radical 3 over 2. And the height? Well, that's still 1/2. So we know the sine and cosine of 150. Sine of 150 is 1/2. Cosine of 150 is negative radical 3 over 2. Let's keep going. Let's rotate that blue triangle 180 degrees. So now it's looking something like that. So notice now we've gone 180 degrees plus another 30 degrees. So this point is the point cosine of 210, sine of 210. But we know those exact values as well. Cosine is the x value. My x value is still negative. So the cosine of 210 is negative radical 3 over 2. And the sine of 210, the y value, now it's not positive 1/2, it's negative 1/2. And let's do one last one. Let's reflect the blue triangle over the x-axis. And now we're going to make this one right here. Again, another 30-degree angle. So in this case, we go a full 360 and then back 30. So yes, this point here now is a 330-degree angle rotation. So this is cos 330. Let me write 330. Sine 330. And even better, you know what those two cosine and sine values are. The cosine is the x value. So in this case, the x value is positive radical 3 over 2. The sine is the y value. Y is negative. So it's negative 1/2. So you know exact values for cosine of 30 and all of its other reference angles. So 30 degrees, 150, 210, and 330. Cool stuff. But wait, there's more. Let's do the same thing, but with a 60-degree angle this time. So now I'm going to draw in a 60-degree angle. So this time my angle in standard position is 60 degrees. We're going to do the same as before. And we're going to call this point cosine 60, sine 60. But remember, it's a 30, 60, 90 degree triangle. So I know that if the hypotenuse is 1, that length is 1/2. The y is radical 3 over 2. So what that does for me is it tells me the cosine of 60. The cosine of 60 is the x value, it's 1/2. Sine of 60 is the y value, radical 3 over 2. Let's do what we did before. Let's do some reflections and rotations. And we'll go the same way, maybe a little bit quicker this time. In quadrant number 2, if I reflect that angle, here's my 60. So I'm going 180, but then back 60. So this is the point cos 120, sine 120. In this case, the x value is negative. So the cosine of 120 is negative 1/2. The sine of 120 is the square root of 3 over 2. If we rotate the blue triangle 180 degrees, here's my 60-degree angle again. So I've gone 180 and then 60 more. This point down here represents an angle with a standard angle of 240 degrees. So this point here is going to be cos 240, sine 240. We know that in this case the x value is negative, it's negative 1/2. The y value is negative here as well. So it's negative radical 3 over 2. And if we do one more, again, this time we go a full 360, but then back 60. So this point is going to be at 300 degrees. And knowing the side lengths of the triangles, the cosine of 300 is 1/2, and the sine of 300 is negative radical 3 over 2. So not only do we know sines and cosines of 30-degree angles and their other reference angles, let's add 60 to it. And yeah, let's go one more time. One more time. This time we'll do a 45-degree angle. All right. So here's my 45-degree angle. And this one might even go a little bit quicker, I think. Because remember, it's a 45, 45, 90 triangle. We know from way back that when the hypotenuse is 1, since it's an isosceles triangle, the legs are the same length. So therefore, this point in terms of cosine and sine is cos 45, sine 45. And since we know now what the side lengths are, cosine 45 is radical 2 over 2, as is sine of 45. Let's reflect over the y-axis. That means the angle, here's my 45, I go 180, let me draw that again, we go 180, but we go back 45. So we are now at 135 degrees. Cos 135, sine 135. And because the x value is negative, cos 135 is negative radical 2 over 2. Sine is positive radical 2 over 2. Oh, and I should have done that in green, but that's okay. And now if we go quadrant 3, we're going 180 degrees plus another 45. Now we're at 225 degrees. The cosine of 225, negative radical 2 over 2. Sine of 225, negative radical 2 over 2. And our final triangle, again, we go a full 360, we go back 45. This is 315 degrees. So the point can be represented as cos 315, sine 315. The x value is positive in quadrant number 4, so it's a positive radical 2 over 2 for cos 315. And the sine is negative radical 2 over 2. Add those to your arsenal. We know a whole bunch of sine and cosine values now. We don't need our calculators anymore. Yay! All right. Okay, let's do a couple more things with this, because we're doing great now. Here's a little thing to remember, this little compass quadrant thing on the right. A nice way to remember where the trig functions are positive or negative. In quadrant number 1, they're all positive. In quadrant number 2, sine is the only one positive, so we'll put an S there. Quadrant number 3, I know we haven't mentioned it yet, but tangent is positive in quadrant number 3. And in quadrant number 4, cosine is positive. So you can remember that however you like. I remembered it by saying all students take calculus. But if you don't want to take calculus, you don't have to take calculus. So a couple of examples in the textbook to show you some of these angle relationships. So if we want to find an obtuse angle with the same sine as 70 degrees. So if it's obtuse, it's going to be in quadrant number 2. So remember, if we go 180 degrees and then we go back 70, that's 180 minus 70. So this sine value is going to be the sine of 180 minus 70, or the sine of 110. That would have the same sign as the sine of 70. Oh no, radian measure, what? Well, let's think about it. We're going to do it the same way. We know pi over 4, that's quadrant number 1. So we want to go not 180 degrees, but we want to go pi radians. So it's going to have the same sine value as the sine of pi minus pi over 4. Oh, can you do that fractional work? Because pi is like 4 pi over 4. And if we subtract 1 pi over 4, we get sine of 3 pi over 4. Can you count by pi over 4s? Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. If we take a look at the next one, now we want angles that are less than 360 or less than 2 pi with the same cosine as these two. So in this time, we're going to be subtracting from 360. So we want the cosine of 360 minus 50, which is the cosine of 310. Or for this one over here, we want the same thing as cosine of 2 pi minus 2 pi over 3. If we get a common denominator, think of 2 pi as being 6 pi over 3. That came out kind of weird. 6 pi over 3. And if we subtract 2 pi over 3, we're left with 4 pi over 3. So let's call this one cosine of 4 pi over 3. And one final thing I want to do. We mentioned that Pythagorean identity before. What we can do is we can use the Pythagorean identity to find the cosine of an angle if we know the sine of an angle. So remember that Pythagorean identity, this is like one method to try. We know that we have this identity here. So what I can do is I can solve for cosine theta. I know sine theta equals 3/5, which means that I want to square 3/5. So let's solve this equation. 3/5 squared is 9/25. If I subtract 9/25 from 1, I'm going to get 16/25. How? If you do 1 minus 9 over 25, it's like doing 25 over 25 minus 9 over 25. So what I get then is cos squared theta equals 16 over 25. This is a squared equation. It's like saying x squared equals. So let's take the square root of both sides. So I get cosine theta equals plus or minus 4/5. So which one do I choose? Remember, theta is acute. This angle is less than 90. We're in quadrant 1. Everything is positive in quadrant 1. So cosine theta then equals positive 4/5. Now, we can do the same thing for the second one, but I want to show you another way to do it. This is a different method altogether. We'll say it's an alternative method. Okay, we can still use right triangle trig here. So what I'm going to do is I'm going to draw myself a right triangle. There's my angle theta. Cosine is adjacent over hypotenuse. So if I can do the Pythagorean theorem, I can get the value of this third side. So this value x equals the square root of 8 squared minus 5 squared. And I think that's 64 minus 25, that's 39. So that third side of the triangle is the square root of 39. Sine, we know, is opposite over hypotenuse. So the square root of 39 over 8. But wait a minute, is it positive or is it negative? Well, the cosine was negative, and it says tangent is positive. If I think back to the quadrants, all students take calculus. Where is cosine negative and tangent positive? It's going to be in quadrant 3. It's going to be down here. So in quadrant 3, sine is negative 2. So then really my value is negative 39 over 8. Because in quadrant 3, sine is negative. Wow, a lot of stuff today, friends. So what are big takeaways? Because we did a lot of stuff. First of all, you should know the sine and cosine of all of these angles, and all of these angles, and all of these angles. We should know their sine and cosine, their exact values. And then we can figure out some reference angles and find some other trig ratios. Whew! That was a fun lesson. That was felt like a workout. Good job.